and sulfide. Those were the 11 you had to memorize. Have them memorized for the final, or write them on your note card. Okay, chapter 4. Let's see. This is covalent bonding, molecular compounds that are held together by covalent bonds. So I didn't even talk about what an ionic bond was. An ionic bond, if you remember from chapter 3, is where it's a bond that's formed from a cation and an anion. And that occurs, you get those things from completely trading an electron. So an ionic bond forms when an electron is completely traded from the cation to the anion. But a covalent bond is different. A covalent bond is formed by the sharing of electrons. All right, so that's how a covalent bond happens. Number of valence electrons needed to gain octet. Oh yeah, this second statement, basically if you want to know for any element how many bonds it would form in a covalent molecule or compound, you need to look at its valence electrons. The number of valence electrons that is needed to gain an octet is going to equal the number of bonds that an atom or an element would form in a covalent molecule. So a great example is nitrogen. Okay, if you have a periodic table handy, you need to look at it, get it out, pull it out. Pause this video if you have to. Nitrogen is main group what? If you've been in my class long enough now, you should know that nitrogen is main group 5. Which means it has 5 valence electrons. Okay, so how many does it need to get an octet? That number means 8. We're 3 shy. So it needs 3 valence. Needs to add 3 electrons to its outermost shell. So remember, let's reread our statement. The number of valence electrons needed to gain an octet equals the number of bonds formed. So nitrogen, goodness gracious. Nitrogen, that's why you see it very commonly with 3 bonds. They don't have to all be single bonds. Okay, you could have nitrogen with a double bond and a single bond. You could have a nitrogen with a triple bond, but these are all forms of 3 bonds. Okay. All right. Polar versus nonpolar bonds. Great problem to work. You will need to know and remember polarity. So this had to do with electronegativity. This is all has to do with this word, electronegativity. All right. Electronegativity, it has to do with an element's affinity for electrons. The more an atom wants an electron, the more electronegative it is. I'm going to say that again. The more an element or an atom wants to get an electron, the more electronegative it is. So guess which elements have the highest electronegativity. Okay? Halogens have highest electronegativity. Why is that? They're 1 away from an octet. If they just had 1 more valence electron, they would have an octet. They'd be stable. So that's why those elements, if you look at electronegativity chart, which by the way, you will get an electronegativity chart on the final. Any table or thing I've given you in past exams, I will give you for the final. So you can look at that, and you need to be able to identify polar versus nonpolar bonds. Now remember, if we have an element, or a molecule of hydrogen, H2. H2 is a diatomic. Oh, by the way, remember your diatomics. We have a hydrogen bonded to a hydrogen. If we look at these 2 atoms, hydrogen and hydrogen, they both just have 1 proton each. Okay, 1 proton on this side, 1 proton on that side. Now, remember that a chemical bond is made up of what? A covalent bond. These guys are both sharing their one electron. Anytime you draw a dash, you form a bond. This is 2 electrons in that bond, okay? Because they're both sharing one. So, when you have a molecule of hydrogen, if you have 2 identical atoms like this in a bond, the nucleus in each atom is equally pulling on the electrons in that bond. Like, again, tug-of-war match. Both sides have equal strength. Protons are positively charged. They're attracted to electrons. So they're going to try to pull those electrons towards themselves. All right, so if you have 2 identical atoms, 2 identical nucleuses, or nuclei involved in the bond, then you have a non-polar bond because the electrons are shared evenly. But if we have an element such as hydrogen and chlorine, let's look at that. Here we have 1 proton on this side in this nucleus. We have 35, I think that's the right number, protons in this nucleus. If we are looking at the 2 electrons in this bond, which side is going to be pulling them harder or with more strength? Obviously the 35 protons. Those electrons are going to be attracted to a mass of 35 positive charges versus just 1 positive charge. Sorry, hydrogen. So that means the electron density is pulled towards chlorine. And now we have a separation of charge. Electrons are not shared evenly. And we call this a polar bond. And to help you remember the word polar, we can draw in poles. So we say this is our partial negative side, this is our partial positive side. Partial negative meaning it is electron dense, partial positive meaning it's electron deficient. Okay, so know the difference between polar and nonpolar bonds. Know also that you can have an entire molecule that's polar. This was a big part of the chapter or exam 2. For example, if we have a molecule such as HCN, this is an acid. We just got done talking about acids and bases. If we draw the Lewis structure for this, we have a hydrogen bonded to a carbon, triple bonded to a nitrogen. We'll get to Lewis structures in a minute. We want to know if this molecule is polar overall. So we got to look at the bonds. What kind of bonds do we have in our molecule? Well, if you do the math, you got to look at electronegativity chart between carbon and hydrogen. Hydrogen has an electronegativity value of 2.1. Carbon has electronegativity value of 2.5, and the difference there is what? The difference there is 0.4. And so that means this bond is not polar because there's not enough of an electronegativity difference. But if we look at carbon and nitrogen, I forget the electronegativity of nitrogen, but here's what I do know. These bonds are polar. So we have polar bonds on one side, non-polar bonds on the other. We also have a lone pair on nitrogen, which means this side of the molecule, if I circle it in pink, this portion of the molecule is electron dense. Because it's a molecule and not just an individual bond we're talking about, we're going to draw a dipole in, pointing to the negative side, and we're going to come back and put a little cross on the other end of the arrow to indicate a plus sign on the sign that is partially positive, electron deficient. Okay, so what things affect polar molecules? Number 1, polar bonds. If you have polar bonds in your molecule, you might have a polar molecule or a molecule with a dipole overall. 2, shape. Remember, if there is symmetry, it cancels dipoles. Whoops. Symmetry cancels dipoles. So you can have polar bonds in a molecule, but if there's symmetry between those bonds or the atoms, then those dipoles, the fact that you have polar bonds doesn't matter. They might cancel out. Not always, but sometimes. 3, do you have lone pairs? Okay, that will definitely be an electron-dense region of your molecule because it's where the electrons are. So if you have a lot of lone pairs, then you definitely have a polar